In this section we're going to look at exponentials and logarithms. Now exponentials and logarithms are used to analyse growth and decay, which occurs in a lot of things in the real world. I'm not going to really talk about that here, but I suppose carbon dating can be used to find age of remains, and that's an element of things you might look at involving exponentials and logarithms. Firstly, before we start, we're going to do a wee bit indices revision. This idea here of a to the power of b, a is called the base and b is the index or exponent, hence the word indices. It can also be used, the word powers can also be used for b. Now, if we want to solve something like 2 to the power of n equals 256, at the moment the only way to do this is to use trial and error. So you would pick a number, try it out. In this case I've used 6, so I'll just could put that into my calculator, 2 to the power 6, and you get 64. That's obviously too low, so you might want to try 7. Try that, and you get 128. Try one up, 2 to the power 8, and 256, bingo, so we've got n equals 8. Now this trial and error technique we're going to use in more detail later on, and particularly the next lesson, but let's have another look at it here. Find the smallest integer value of n such that 4 to the power of n is greater than 10,000. So try 5. You can pick any starting point. Some starting points will take longer to get the answer than others. But I've picked 5 here, and it came out at 1024, so that's too low. Try 6, 4096. Try 7. Okay, that's the first value of n that's given an answer here that's greater than 10,000. So the value of n equals 7. Now if you jumped straight to 7 and got this answer, don't trust in that. I would always test 6 out. Try one before, just to make sure that 6 didn't give you an answer of greater than 10,000. Now, just to remind you of an exponential graph, again we've looked at this in Unit 1, but just a wee quick reminder. This is an exponential graph here. This one's f of x equals 2 to the power of x. To plot this, you could do a table of values. You could use x as 3, so 2 to the power 3, that gives you 8. 2 to the power 2 gives you 4. 2 to the power 1 is 2. Remember, 2 to the power 0 is 1. Anything in fact to the power 0 is 1. And the way to get the negative values is to think of your indices from differentiation and integration. A negative power, then you take it below, and it's the same as writing 1 over the number to a positive power. So 2 to the negative 1 is the same as 1 over 2 to the power 1, and 2 to the negative 2 is the same as 1 over 2 squared, and so on. 2 to the negative 3 is 1 over 2 cubed, and your graph will appear like this. Now there's two main points in the exponential graph to take note of. This point here, which is always going to be 1. It doesn't matter what we have here. If you've got a 0, 3 to the power 0, 4 to the power 0, you're always going to get a 1. So any exponential graph always goes through 1. Another point to note is this point here, 1, 2. This comes from this value here. So 2 to the power 1 is 2. And if you were to draw the graph of 3 to the power x, and you put 1 in, this would be 1, 3. And 4 to the power x, that would be 1, 4. So this value is always dead easy to work out here, because this here, the second part, is just the base. We can look at that in action and see that if we draw 3 to the power x, the graph goes through 0, 1 again, because if you do 3 to the power 0, you get 1. And also, when you put 1 in here, you get 3 in your y-axis, so that value here is 1, 3. Same idea for the negative powers. This is going to be 1 over 3 squared, isn't it? It's going to be 9. It's going to be 1 over 3 cubed, 1 over 27, and so on. Finally, just a wee note on different exponential graphs. This is the graph of y equals a to x where the base is greater than 1. That's an example of a growth function, and we'll look at that in the next slide. And here, when a is a fraction between 0 and 1, then we get a decaying function going down the way. Notice that it still goes through 0, 1 and 1a, i.e. the base. Where are these things likely to occur, exponential functions? Well, human population, it's always increasing exponentially. Viruses, a virus starts off small and then spreads dramatically and gets much bigger. An avalanche, feedback on a guitar, starts off small, gets very loud very quickly, and some other examples there for you to look at.